Okay, so in this example, I'm going to elaborate a little bit more on tangent vectors, and from tangent vectors I'm going to sort of derive or show you the concept of a normal vector. Okay, so here we have this parametric curve again in three-dimensional space. It's defined by this parametric equation right here, and I have a little part of the curve shown. This point right here is the point 0, 0, 2. It's at t equals 0. Okay, so I plug in 0 for t, each of those components there. And then this point here is where t equals pi, and it's the point 0, 5 pi, and 2. Okay, so I want to find a tangent vector, a vector that's tangent to this curve at t equals pi over 2. Okay, so if from t equals 0 to t equals pi, we go from that point to that point, then halfway, pi over 2, would be a point somewhere here, halfway along this curve. Tangent vector is pretty simple. I'm not going to talk too much about that. Basically, with a normal curve, like on a two-dimensional curve, the derivative tells you the rate of change of the curve at a given point. Also, same thing with the tangent vector. The tangent vector is a vector that's tangent to the curve, and it points in the direction of travel along the curve, and it tells you basically how fast you're traveling along the curve at that point. So if I zoom in at a point, and let's say that this is the point that I'm interested in, the tangent vector, which I'm going to call t, it'll be a function of t because it depends on where you are along the curve, and it's a vector that's, like I said, tangent to the curve at that point. So I should clarify, these are going to actually be unit tangent and normal vectors, so they'll have a length of 1. If I just wanted any tangent vector, all I would have to do is let's call that like t sub a for any tangent vector. It would just be the derivative of my parametric equation. But if I want the a unit tangent vector, then you guys know to make a vector unit length, you divide it by its length. So let's go ahead and do that. I'll take the derivative first. So the derivative of the x component is just 2 cos t. The derivative of the y component is 5, and the derivative of the z component is 2 sine t. And when I divide by its length, it is just move it over here and give me a little more room. Okay, so the first component squared, 4 cos squared, plus the second component squared, plus the third component squared. Okay, so you should see that, I can simplify this, factor out the 4, sine squared plus cos squared equals 1, so I just, for my tangent vector, I get 1 over root 29, and then this. Okay, so that's great. Okay, so that is a vector that's tangent to the curve along the entire length of the curve. So we're interested in when t equals pi over 2. So if I plug that in, and cos is pi over 2, that's 0, 5, and negative 2. Okay, so let me expand upon this and tell you guys about normal vectors. Okay, so I want to reuse this space here. Stick our tangent vector over there. Okay, so a normal vector is a unit normal vector is a vector that is normal to the curve at a point, therefore normal to the tangent vector, and since it's unit vectors of length 1. Okay, so from the tangent vector, there's a couple of ways that we can come up with the unit vector. If we know the axis that we want to rotate the vector around, we can multiply it by like a transformation matrix and rotate the vector sort of like manually that way. But I just want to show you guys a property of the tangent vectors, and it will lead us to another way to calculate the normal vector. Okay, so I just want to show you what happens if I take the tangent vector and I dot it with itself. Okay, well, when you dot a vector with itself, you just get the length of the vector squared, and ignoring the fact that we're talking about a unit vector here. Okay, so ignoring the fact that it has length 1. So let's just say that when I dot the tangent vector with itself, I just get some number. Okay, what happens if I take the derivative with respect to t? Okay, so one of the properties of the dot product is something similar to like the product rule with normal derivatives. So when I take the derivative of a dot product like this, I can take the derivative of the first vector, dot it with the second vector, and then add the first vector, dot it with the second vector, and the derivative of a constant is 0. And since it doesn't matter the order in which you compute a dot product, I can flip this one around, let's say, and say t dot it with t prime, add them two together. So I can say that I end up with two t's dot it with t prime equals 0. Divide through by 2, and you can see that the tangent vector dot it with the derivative of the tangent vector equals 0. And this is an important result because it shows us that the derivative of the tangent vector is orthogonal to the tangent vector, and that's what we want for our unit normal vector. Since we just showed that that was true, then because of the properties of vectors, we can say that the unit normal vector is actually the derivative of the tangent vector divided by the length of the derivative of the tangent vector. So now that we know this, we can calculate the normal vector. Okay, so it's a function of t, so it's the derivative of the tangent vector. Oh, I erased it. Okay, so that would just be the second derivative of this thing here. So that would be squared. And again, we can, we can factor out the 4. Sine squared plus cos squared is 1. Take the square root of 4, and to save space, I'm just going to rewrite this as a half. Okay, so that means that at pi over 2, our normal vector is going to be 1/2. We'll have minus 2 there, 0, and 0 there. So, just to show that these two guys are in fact orthogonal to each other, we'll test it. Let's compute the dot products of these guys. So hopefully you can see right off the bat, the x component of this dotted with or multiplied by the x component of this, 0. X, y, and z components of this multiplied by the y and z component of this, 0. So you can see that the unit tangent vector and the unit normal vector that we obtained are indeed orthogonal.